Okay, so I'll warn you in advance that this is going to be a slightly dull lecture because I'm obliged to set up some facts which are not very exciting or illuminating. And it's more or less on the same lines as what I did last time. What I did last time was to discuss Gaugino-Higgsino mixing, and I'll complete that in a few minutes. And then we'll talk about other kinds of mixing that take place in the MSSM. Now, before I do any of that, I just want to go briefly over. So I'm going to go over things I did last time just a little bit. The first thing I want to go over is these supertrace identities which we derived last time. And if you remember, last time we showed that the supertrace of the up quark and down quark superfields added up to 0, as well as that of the electron and neutrino superfields added up to 0. And that is in the MSSM. That crucially uses the charge assignments. The fact that there are two possibility terms, one for the hypercharge and one for the 3-component of SU2 after the Higgs mechanism, and the charge assignments under these two are all known. And if you write them, you find that these identities are true, although this for any one of these individually, which is equal to summation STA web of TA minus 2, this is not equal to 0. So for example, we found concretely that this was some non-zero thing and this was another non-zero thing which was equal and opposite, so that they added up to 0. Now this seems slightly miraculous because it arose after we did a certain calculation involving all the field content of the MSSM, and personally I don't actually know why it happens other than by doing the calculation. But there's a much less miraculous identity which is much easier to derive and depends on less details. And that occurs if I sum over all possible quarks and electrons in one generation, which means I take the supertrace of this plus this plus this plus this. Okay, that I can show you right away has to be 0. So the summation over all quarks and electrons in a single generation, supertrace m squared, this is equal to minus twice. Now we have sigma summation over A, and then summation over all quarks and electrons of trace T. So this is for a single supermultiplier, but this is the sum over all quark and electron superfields, and we get this kind of answer. But now you notice that inside it is the sum over all quarks and electrons of the trace of TA, where TA is a U1 generator, and by anomaly cancellation, this just has to be 0. This is just the absence of the U1 anomaly. That contribution which is linear in the U1 charge, which technically comes from the gravitational coupling of the U1 photon. So it's like a triangle diagram with one photon externally and two gravitons. Okay, the triangle with all photons externally gives you a trace of TA cube, which also adds up to 0. We have done all these calculations in the beginning of the course, but that doesn't appear in this D-term equation. Trace of TA is what appears. And because the standard model has this stringent requirement of anomaly cancellation, this quantity in the box must be 0. So the sum over the supertrace of everything in one generation is anyway 0. Okay, regardless of the miracles required to make this identity. And that being 0, at least from this you can make the weaker statement that at least one squad or lepton is light. That's okay. Yeah, I think that is better. It does. Yeah, it doesn't work. You can see ahead sometimes in the video, but okay. Oh, this. Yeah. But what? Oh, here's Tata. It's all right. It's all right. Okay. Are you embarrassed? Where's he going? I see. You would have been better off coming here somewhere. Anybody who is listening to this course doesn't have that much of constraint on their time. Okay. So anyway, to summarize what I did here, last time I calculated these two super traces added over up and down quarks superfields or over electron and neutrino superfields, and we saw that you get some non-zero answer for each of these four things, but this plus this adds up to 0 and this plus this adds up to 0, and that makes an exact sum rule with 0 on the right side, which clearly violates phenomenology because it tells us that up and down quarks, one of them has to be light, and here that one of these selectrons has to be light.
And that was true assuming spontaneous.
That was true assuming spontaneous symmetry breaking. And that led to the fact that you had actually two d terms, one from the hypercharge and one from the 3-component choice. Okay. But what I'm pointing out just now is that a much less miraculous identity obtains if you sum up supertrace m squared over all quarks and electrons in one generation, which really means all of these added up. That's obviously 0 by anomaly cancellation. It's a weaker identity. It's implied by these two, but doesn't imply them. But it's good enough or bad enough. We're supposed to be convincing ourselves that with such identities we can't have spontaneous supersymmetry breaking coming from the MSSM. So this is just a little rerun of that fact. This is one comment on last time. The second comment on last time is that we introduced at some stage soft SUSY breaking terms, and we didn't go in detail into the rationale of what makes them soft, but we said, well, if they're super renormalizable, then they have a chance not to upset the ultraviolet behavior of the MSSM whose operators, which has the sector which has supersymmetry. That if this SUSY breaking sector has dimension 4 operators in it, then that's likely to upset the ultraviolet behavior. Now the fact is that even with dimension 3 or less operators, there are possibilities for such soft terms by loop corrections to upset the ultraviolet behavior, and I'd like to give you an example. So example, it is a little bit illuminating, of an apparently soft term that's not really soft. This answers the question, why don't we just write all possible dimension 1, 2 and 3 couplings in the soft Lagrange. Okay. So the term in question is phi squared phi star, which in fact I didn't include in my soft Lagrange. By this I mean something like some coefficient alpha I j k, phi I, phi j, phi k star. In other words, these three fields don't have to be the same. They just have to be some three scalar fields. Let's assume such an interaction exists in the theory. Then potentially we can get a tadpole like this. Okay, and this will contract phi j and phi k star, let's say, with an I outside. So it will be a tadpole for phi I. Notice that this can't occur if this was phi I, phi j, phi k. Can only occur because one of them is a star, and therefore its propagator contracts it with one of the other two. Okay, so phi I, phi j, phi k is safe. This is possibly unsafe, but we can say more. This will be allowed only if phi I is completely neutral. That means neutral under the entire gauge group. That's pretty clear, because if phi I is not completely neutral, then this dipole violates the symmetry of the original theory, which is charged, for example, U1 or whatever, and then it must be 0. It must automatically turn out that when we calculate this thing, we get 0. Okay, but there's no symmetry protecting it if phi I is completely neutral. So whenever one of these is completely neutral, then such a term can lead to such a dipole. Now, what effect does this dipole have? First of all, well,
it's quadratically divergent.
Exactly, that's exactly right. So, effect of this dipole is that if the vertex was lambda 3 times phi squared phi star, 3 for cubic, this is the temporary notation, this is the coupling, then the dipole gives lambda 3, which comes from here, times the ultraviolet cutoff squared times the dipole. Okay, lambda 3 is of scale dimension 1. Lambda squared is of scale dimension 2, so the whole thing is scale dimension 3, as you expect from the coefficient of a dipole. Okay, but this is a quadratic, and this comes of course from this loop integral, which has got one propagator, so it's quadratically divergent. Okay, and so this is a quadratic divergence, and quadratic divergences are the entire thing that we invented supersymmetry to get rid of. So the last thing we want is for them to come back for any reason. And here is an example of a very innocent looking term which can make them come back. Okay, so I wanted to make this point. However, in MSSM, such fields don't exist. There is no scalar field in the MSSM which is completely neutral. There is no possible dipole. There is no scalar. Neutral means completely neutral. Even if it's neutral under U1, it won't be neutral under SU2. So there is no neutral scalar. So actually, he is actually soft. In MSSM. And I didn't add it so far, but what we'll do is we'll wait until it plays some role and then we'll see whether it can be added. Okay. But this is a slightly subtle point, because this point depends not just on supersymmetry but on a very, very specific field content of the MSSM. And this course is not really only on MSSM. I think we could be studying more general models, and we obviously need to if we are talking about LHC and so on. So I just wanted to show you this. It's just an observation for now. Hopefully we'll have some use.
So this can actually be written good, is that right? I mean, what about SU2 contours?
Yeah.
So you have half cross half.
Well, the point is that remember these are some scalars. They could be any scalars. So for example, they can be right-handed squawks and leptons. Those are SU2 singlets. So those are always allowed. Okay. Now, of course, those are charged. But then under the left-handed thing, some are charged, some are neutral. So I believe if you really try hard, you can probably rig up some cubic coupling like this. You're allowed pretty much everything. I think if you allow one Higgs and one left and one right fermion, I think you can probably do it. Actually, don't know. Probably worth trying. Okay. So that's one observation. The other observation from last time that I want to quickly recap is the reason I'm...
So I just understand that your honest soft terms are those terms which added to the Lagrangian lead to no divergence.
That's no quadratic divergence.
But log divergences are
log divergences. Yeah, I think they are allowed to lead to log divergences.
linear divergences never happen.
Yeah. Okay. Now last time we did this thing called gauge-Higgsino mixing, but we didn't complete it. I'm not going to repeat what we did except to say that it's in two parts. One is charginos. These are the ones obtained by mixing the charged gauginos with the charged Higginos. And the other are neutralinos, which are obtained by mixing neutral gauginos with neutral Higginos. The interesting thing is that standard model has precisely equal numbers of charged gauginos and Higginos, so they have completely different origin, and also equal numbers of neutral ones. So let's just remind ourselves of that fact. So here the Lagrangian responsible for mixing is minus so I've assumed that the Higgs develops its wave, the H1 develops a wave V1 in one of its components and H2 develops a wave V2 in the other of its components. Then these are various mixing terms. Remember, these are all fermions. The tilde means they are fermionic partners of known particles. This is the Vino of plus charge. This is the Higgsino from the first Higgs. This is the Higgsino from the second Higgs. This is the Vino of the opposite charge. Notice that these are all the charged gauginos and Higginos. Okay, there are two of these and two of these. We are not counting the Buinos in this discussion because they are strongly interacting and they don't mix with Higginos. So they are out of the story. So this is the mixing, and this part of the mixing comes from superpotential terms, which are of the form, not superpotential, excuse me, these come from kinetic terms of the Higgs. These are of the form capital H dagger, capital H, e to the V. Okay, if you pull out things, you get this. Okay. In addition, there are contributions from the soft SUSY breaking term, which allows a soft mass for the Vino. So that's certainly there. And then another one, which is back to the supersymmetric sector of the theory, which is the famous mu term linking H1 with H2, capital H1 dot capital H2. That was part of the original superpotential, and if you pull it out, we'll get this. So you see this nice structure, W tilde plus and minus, H tilde 1 minus and 2 plus. These are the four guys which mix. Moreover, you can create, so in the case of W, these are each other's antiparticle. In the case of these, they're not, but you can presumably, actually now I'm suddenly puzzled about how many different particles there are. You have H tilde 1 minus, what is its dagger? Yeah, I think finally there is the same number of states because there is really no H tilde 1 plus. Everybody has a CC here, so those are the other ones. Okay, even these W tilde plus and minus have their dotted. The point is that the dagger of this will be a dotted spinner, so you don't have to worry about that. That will be in another sector.
So neutron also has a CC.
Yeah, everything has a CC. This also has. Both these terms, this and this have a CC. All fermion mass terms have a CC.
So actually, I asked
Yeah.
back the question. So W tilde is the supersymmetric partner of the SU2 gauge bosons?
Yes, W plus and minus, the two charged ones.
So these things are in the tree of SU2.
That's correct.
Okay.
But this is after the Higgs mechanism, so now they're just charged under the U1 electron.
I see, but suppose that happens in the Lagrangian.
Yeah.
Okay.
So they are linear combinations of the guys with the index A where A goes over 1, 2, 3, but they are the 1 plus I2.
Good. And the H tilde and the two Higgs were in both the half of SU2?
Yes, that's
okay.
right.
So you've got half that plus half is equal to 1, which is half of the Higgs. Okay.
That's right.
And
but I mean, before the Higgs mechanism, these did have different quantum numbers.
But you could couple this. This was part of some.
Yeah, the reason this was part of something is that this was a field at that time.
This was
and then of course it was a legitimate coupling. This was a half, and this was a half.
So half plus half gives you 1, 1 plus 1 gives you 0.
Exactly. So these were of course all originally, these were in fact just the, as I said, this was in the supersymmetric language, the capital H Higgs field and its dagger, and e to the vector superfield in the middle.
So this was already in the supersymmetric Lagrangian.
Yeah. So this was in the supersymmetric Lagrangian, so was this, so was NCC. This is a soft breaking term. This is back in the supersymmetric Lagrangian.
Okay. So you also please remind me that the two things are identical in charge, in SU2 charge content.
They are actually conjugate. If one transforms like an SU2W, the other is like an SU2C.
Right. Okay.
WC. Conjugate. Charge content. Okay. Then last time we went through all the various stuff and we found well, it's hardly a big deal to take this whole thing and just diagonalize it. And you get basically two mass eigenvalues. And we made the comment, which for this you can look up the previous lecture. The comment was that there are three basic parameters here, mass parameters, the mu term, the mass of the Z, and this is M2, excuse me. And these V's, which actually get summarized into the masses of the W and the Z, which are anyway of the same order. Okay, so the comment was that the interesting limits are when mu is much larger than M2 is much larger than MW and MZ. In this case, as soon as MW and MZ can be neglected compared to these scales, I'm sorry, my 2 is really not very clear. This is the 2. This is a soft breaking mass. It's not so in this limit, you can neglect these guys, but if you notice, these are the guys responsible for mixing between the gaugino and Higgsino. The rest of these two terms are diagonal, okay, which means that the charginos in the limit where this can be neglected are really gauginos and Higgsinos. Moreover, the lightest one, which plays an important role in phenomenology, will be the one associated with M2, which is a gaugino. Okay, so in this case, lightest chargino is a gaugino. Okay. And if I reverse the first two limits but keep this still the smallest, that is M2 is greater than mu, greater than MW and MZ, then the lightest charge is a Higgsino. This guy is the lightest charge. Okay. So this was the comment last time, and the next thing to do is to repeat this exercise for the neutralinos, where there are no great surprises. It's very similar, except that the mass matrix analog of this, instead of being 2 by 2 in a complex basis, is 4 by 4 in a real basis. And in fact, the corresponding terms can be easily read out, but I'll write them anyway. So neutral for neutralinos, we have minus d2 by 2, w tilde 3, if there's any question about notation, please ask, because it's important to have these things clear. What you see basically is that instead of w tilde plus and minus, what appears here are w tilde 3 and b. This is the B-no and this is the neutral B-no. Okay. Now according to P-up, that's right. This is correct. Writing it perhaps in a more redundant notation than necessary. Now there's again plus CC of everything. But this time the hypercharge GY also enters because of the B-no. Then there's an analog of this term, the soft mass, there's first of all an analog of this term. I think this seems to come out plus now, and it is H1 tilde 0, H2 tilde 0. H1 dot H2 being an SU2 singlet has to either pair H1 minus with H2 plus or H1 neutral with H2 neutral. These are the up and down components, and because of that epsilon AB in the contraction, the relative sign is opposite. And finally, this again plus CC and minus a half, and now we notice that there's M2 for W3, W3. the same M2 parameter which was there by SU2 gauge invariance for the other Benos, but the parameter for the Beno is totally independent, not constrained by. So in this Lagrangian you seem to have a few more parameters. In place of M2 you will get M1 and M2, and in place of M, eventually we have managed to rewrite all this in terms of MW only out of these two, but here we'll have to use both, either both. Now here we'll use MZ.
So
Anyway, they are related by sign by Weinberg angles. Yes.
Neutral means neutral under electromagnetism?
Yes.
So these are the Higgs is that neutral under electromagnetism are the guys that have condensed.
That's right. Exactly. Thank you. So these guys are the guys whose waves are those. Okay, so these are these are not the Higgses, these are the Higgsinos. So these are the super partners of the guys whose waves are those.
And what is B?
B is the Beno, so it's the fermion partner of the B mu gauge field, which is the 3 component of the SU2 triplet. Okay, so it's the one which. Sorry. Excuse me. That's what I said is true of W3. B is the hypercharge. So there are 2 U1 gauge fields that corresponding to them. There are 2 neutral gauginos. The one for hypercharge is the Beno, and the one for the 3 component of SU2 is W. Yeah. Tell me. It's always possible I got it wrong anyway, but yeah, what? Which sign? These
it is probably due to this epsilon.
Here, Yes. Anyway, these particular set of formulae are all copied from DGR, so there is not. So you can always go look them up. Okay. Now here we notice that again. So from this, it's very easy to write down the 4x4 mixing matrix, which connects P tilde, W3 tilde, the 2 neutral gauginos, and H1 tilde 0, H2 tilde 0, which are the 2 neutral Higgsinos. So it's a 4x4 matrix, and I'm not going to bother you with writing it down and still less with diagonalizing it. But we'll just notice that again, mu much greater than this time M1 and M2, much greater than MW and MZ. Here, this again implies the same conclusion as there. Lightest neutralino is a gaugino. And again, you can see that in this limit, if we can neglect MW and MZ, that's the same as saying we can neglect these Higgs waves, because these MW and MZ are just proportional to V1 and V2 combinations of that, which means mixing is gone. These terms are all diagonal, which is the same, which is the reason why then the lightest neutralino is dominated by gauginos, and then the reverse when M1 or 2 greater than mu, greater than MW and Z, then lightest neutralino is gaugino. So these are all facts which will have phenomenological consequences.
So there could be a hierarchy also between M1 and M2.
I suppose there could be. I mean, this is why phenomenology is such a hard subject, and there could be everything. It's just one could go on listing various cases. I guess what usually happens is that somebody notices one of the cases is interesting and pursues that. But one could try to ask what would happen if you took a hierarchy between M1 and M2. The general rule, though, is that if you don't take anything like one of these limits, then there's mixing, including possibly a lot of mixing. For example, all these things are of the same order, there's huge amount of mixing.
So mu was a term with the superpotential.
Yes.
So M1 and M2 are the only.
M1 and M2 are the soft breaking terms. Okay. Now, this much was about mixing of gauginos and Higgsinos. So that completes our discussion. We completed it, but we've left it slightly hanging in the air because you might say, so what? I haven't told you what good or bad this does for physics, but there will be many such results which will hang in the air till we can use them. And now I want to turn to another kind of mixing which is much more complicated, but we can sort of see a little more clearly what kind of physics is going to give rise to. This discussion is connected to my last lecture in the sense, once I finish writing MSSM, Lagrangian and the soft breaking terms, we've got all the mass terms of every particle in the standard model, and therefore we have all the possible mixings that there can be, and therefore we have to worry about them one at a time. Now, nothing very exciting happens as far as mixing between the different electron generations and quark generations. It's basically similar to the standard model. There may be small differences, but we've already looked at mixing among electrons and mixing among quarks. Actually, there's no mixing among electrons in the approximation we are working with, which is that right-handed neutrinos are massless. Okay, so we actually haven't looked at mixing among electrons, but we've looked at it among quarks. That's the CKM matrix. Okay, now we found a new mixing, which is that among gauginos and Higgsinos, and now finally we are going to find the most complicated and unpleasant mixing of all, which is mixing among fermions, which I hope you all remember are scalars. Okay, and the problem is that once we've introduced supersymmetry, then the three generations of quarks and electrons are mirrored by three generations of squarks and sleptrons. Okay, and squarks and sleptrons, not among each other because that would violate color, but within themselves they can all mix like crazy. Okay, so let's look at sleptron mixing, for example, and later we'll look at squark mixing. The point here is that the mixing among leptons is not the same as the mixing among leptons because we've introduced soft SUSY breaking. If we hadn't done that, then supersymmetry would tell us that the mixing matrix for leptons is the same as that for electrons. That would be the end of that discussion. But the soft SUSY breaking Lagrangian has all kinds of potentialities for mixing up some of these and not the others. Okay, and we'll see its contribution repeatedly in this. So what I'll do to show you how leptons mix is to write down all relevant mass terms, all relevant terms in the MSSM plus soft Lagrangian. And by relevant, I mean there will be terms which after Higgs mechanism produce selectron masses. That means masses for the selectrons and the neutrinos. And to remind you, there are two kinds of selectrons, the left selectron, which is a superpartner of the electron, and the right selectron, which is a superpartner of the right-handed electron. But there's only one kind of neutrino, which is the left neutrino, because we are assuming that there are no right neutrinos, therefore there are no right neutrinos. Okay, so in the electron sector, there are these three objects. Okay, and despite their names, some of them being named left and right, they are all scalars, so they can all mix very happily among each other. And that's a pretty awful thing to contemplate, but here it is. So let me write down all the contributions and let's write them down organized by where they come from. So now, unlike there, I'm looking for terms in the scalar potential of this plus this. Okay, what contributes to the scalar potential? There are three contributions: the F term, the D term, and the soft breaking term. These are three independent contributions to the scalar potential. So let's write the F contributions. I'll write it. I'm not going to derive every detail, but I think you can sort of read off where they come from, and we'll try to do a few exercises to keep ourselves in shape, reminding ourselves where they come from. I'll just write a few. I'll write all the F terms and then we'll. The notation is horrendous, but with a little bit of effort we can decipher everything. that's the last term. Repeated indices are summed. Okay. So where do all these terms come from? If I tell you that, it's not hard to figure out what the terms mean. They all actually come from only two sources, and you can detect what the source is by looking at their numerical coefficients. So all come from mu h1 dot h2 minus fij e. Since these are f terms, I only need to identify for you what term in the superpotential produces them. Okay. Then what you're supposed to do is differentiate that superpotential field by field and then mod square it and add it. And you should see immediately where this comes from. So these are the two Higgs fields. This is the left-handed electron doublet, the right-handed electron singlet, rewritten as a left-handed positron singlet, as we always do in supersymmetry. And H1 is the Higgs field which gives mass to electrons, and one of the two types of quarks. H2 doesn't appear in the electron sector. It only appears in the quark sector. Okay, so from here can one see where everything there comes from? For example, differentiating in H1, I'll get mu H2, which is here as well as here, different components. Depending which component of H1 I differentiate in. Likewise, I get a left and a right coupling. So it's a left selectron and a right selectron. In this case, it's a neutrino with the right electron, and here it's a left electron with the right electron. Okay. And these mixing matrices are built in. So the first two terms are obvious. They come from differentiating in H1. Okay. If I differentiate in H2, then I only get the square of mu H1. That doesn't seem to be what I'm seeing here. What I've left out one term probably. This term, oh sorry, if I differentiate in H2, I don't get a selectron term, so I just don't write it. If I differentiate this in H2, I get some mass for the Higgs, but I'm not calculating that. I'm looking at selectron mixing. Okay. If I differentiate in the left-handed left-handed positron, then I get H1 dot Li, the dot being the SU2 contraction, that's here. Okay. And then if I differentiate in one or the other component of this guy, one of them is a neutrino and the other is a electron. The two components of the left-handed electron doublet, and I get these two, and the way to identify them are that they should both be properly charged. Of course, they are neutral after I mod square them, but in this case, I have obviously differentiated with respect to a charged guy because this whole thing is still charged. This is a charge +1, charge 0. Here is charge +1 and -1, so this must come when I differentiate within the nucleus, in the symmetry. That's how it is. So if you got all this, then you will surely buy the rest of it. So I can run, yeah.
So H1 does not mix with any other field or that's
yeah.
That's why you
Yeah. Yeah, it would have been worse if Higgs had mixed with fermions.
So all the H1 dependencies here are higher than that.
Yes. Okay, so all come from this. The next thing to write is the D terms. And these are 1/4. They all have manifestly the structure of D terms. For example, H1 mod squared minus H2 mod squared times summation over I. You can see that this is the hypercharged D term. That's given away by the presence of the 2 here. Hypercharge of 2 or -2, whatever it is associated with right-handed electrons. Okay, and then there is the other D term with G2 squared appearing in it, and this has more the look of a SU2. Good. So all these are all potential terms as yet. For example, none of these are mass terms. These are all quartic couplings, which is what D terms normally are, and without the phi Laplace parameter. But the point here is that both in the F terms and in the T terms, H1 and H2 some component will get a wave, and I have written all the terms from where you can read off masses. The third contribution is actually the simplest, the one from the soft breaking term. So this is F, that's D, and then soft. For that we just open our notes and we copy out whatever we have written. So it's L, I, L star, M square L, L, everything filled up, leptons. So this is the soft mass terms for the left-handed leptons. Then the left-handed positron or right-handed selectron has its own term independently. It's a good point to remind you that I told you this lecture is recording.
The 9 independent components of the first thing?
Yes. And finally, H1 dot. So here's again a soft term. This is of the form phi I, phi j, phi k. You may wonder what the star is doing, but really ER star is a member of a chiral superfield, because ER is the partner of the right-handed electron, but it's the left-handed positron that is in the chiral superfield, and its partner is EJR star. So although superficially this looks like phi 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 star, it's really phi 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 in a basis of chiral superfields. That's the end of it. These are all the terms. Now what we have to do is give all of these H's, H1s and H2s appearing everywhere have to be given waves. Some of the terms like these already are mass terms, and some of these will turn into mass terms as soon as the H's get waves.
So what are the FEs and the EE?
Yeah. So last time I introduced this part, sometime before. What happens is that this is an arbitrary coefficient which in principle has three indices linking phi I, phi j, phi k. But one of them has to be a Higgs. Therefore, that coefficient isn't there. Therefore, it's a matrix in two indices. It's an arbitrary matrix, but in the supersymmetric part, we had a matrix Fe, which parameterized the Higgs couplings. And so we parameterized this new arbitrary thing by its difference from Fe by another matrix AE. So if AE is 0, then this term isn't there. If AE is 1, then this term is comparable to the term coming from the supersymmetric sector.
So are there 36 new parameters?
Yeah. This is the whole point of, that's exactly right. The 105 parameters of the MSSM plus soft, the 105 extra parameters are all in the soft Lagrange. The point is that the supersymmetric MSSM doesn't have too many new parameters, because after all it's a supersymmetrizing, and the only new thing there is the Higgs. There's an extra Higgs. So there's a little bit of extra freedom, but it's not very much. A few things become more independent, and then there's the new term H1.H2. But it's the soft thing which is all supposed to be derived from some unknown high-scale theory, which brings in 9 plus 9 plus 9 every time you do something, and so you end up with 105 new parameters. So these are those.
So in the Gauge-Higgs sectors also there could be cubic soft terms.
In the gauge, no, because of R parity. Cubic soft term, here is a cubic soft term. You go in the gauge
sector, like the ones that you described earlier.
Yeah.
About the charging and mixing and so on.
Yeah, it was there, right? In the gauge sector, I wrote Well, this time I wrote only the thing after having a web. Last time when I did that, I had actually written the thing before you gave a web. The point is that here I have written down for you some interactions with H still being fields. But if H1 became replaced by a V1, then it would be the analog of what I wrote for Gaussian and Higgs in the beginning of this lecture. But if you look at the last lecture, you'll see that we had cubic couplings which then became these.
Cubic couplings are going to be fermions always dimension 4 on it.
Yes.
So,
in the soft?
Yeah.
Sorry, I misunderstood the question. The question was why don't we have those cubic couplings in the soft piece? Oh, that's because exactly what we said. They're not in the soft piece. The soft piece allows basically only cubic couplings among among complex scalars, and for the reason I showed you with the tadpole, generically not involving their complex conjugates. And so here's an example of that. But so this is the reason it doesn't come in for the Gaussian and Higgs is that they are fermions.
In these d terms, have we assumed the eta?
Yeah, we seem to have assumed the etas to be 0 at the moment.